Hello and welcome to Group 8's presentation on Spotify for IS6420. Group 8 consists of Patty Corrigan, Ray Chen, Kavya Katuru, and myself, Nick Tingy. For this presentation, I will start out with an introduction to Spotify and some of the database requirements, followed by Ray, who will walk us through the conceptual model. Next, Kavya will describe the logical model and Patty will take us through the physical model. I will then end with a project summary. Spotify is the largest music streaming service in the world. The reason we chose Spotify for this project is because streaming services like Spotify are such a huge part of modern life. It's a part that we all enjoy, so we wanted to explore what the backend might look like for Spotify, at least on a basic level. Spotify was launched in 2008 at a time when Apple dominated the music industry. Music streaming had been a thing for quite some time through Pandora, but Pandora was more like radio reimagined. Then Spotify splashed onto the scene and has quickly grown to be the largest music streaming service in the world, with a $27 billion market cap and over 270 million active listeners per month. Spotify's current catalog has over 50 million tracks. With an average song length of 3 minutes, that is over 285 years of music. It is available for free with limited functionality and choice, and the premium option allows downloading content for offline use. Spotify offers streaming audio, including music, podcasts, and radio content. Some of the features that have made Spotify so popular include a personal library, playlists, and the ability to connect and share music with friends. Spotify also allows users to download their music for offline listening, one of its more substantial offerings. This allows Spotify to contend with companies like Apple and Amazon that sell physical copies of audio content. Spotify also provides music feeds, including new music bulletins and concert news. What makes Spotify so interesting for this project is that the business Spotify is in is data. Think about it. You can have a $27 billion company that doesn't produce or manufacture anything. What Spotify does is distribute data. The entire business is data storage and management. This requires excellent systems for data storage, organization, and very efficient and accurate querying mechanisms. The whole business is an exercise in database management, which makes it perfect for a project such as this one. Spotify is very nimble on the OS and hardware side as well. It is available on Windows, Mac, and Linux. It is available on various mobile platforms such as iOS, Android, and Windows, and this is likely a primary use of the service on mobile devices. For a service such as Spotify, it was quite an exercise to imagine what ideal requirements would cover the overall functionality of the software. Users would have to register an account, of course, since the individual user experience would require almost all settings and audio content to be tied to a user ID. The database would have to store information about artists, albums, and songs. Users can create their own playlists and libraries, so the database would need to store those relations and tie them to user IDs. This basic functionality is the highest priority. There would need to be a payment system with tables of financial information, and there would also need to be relations set up to handle the user's social network and radio preferences based on the content in their playlists and libraries. Considering the breadth of what Spotify offers, we narrowed the scope to the basics: the user profile, the music itself, and the almighty playlist. This means any artist, any song, and any order, and that it is all tied back to the user and is fully customizable. This basic functionality would allow users to make a playlist of their very own titled Songs to Build Playlist Databases To, consisting entirely of songs by the band The Algorithm. Yes, it is a real band, and yes, they are awesome. In order to offer the basic functionality in the scope of our project, we specifically modeled the storage of user information and the creation of storage of playlists. We narrowed down the prioritized requirements to the relations user, playlist, track, album, and artist. To allow for multiple artists on the same track, we also added the performance table. Well, that's it for the introduction. Spotify is truly an amazing company. Now Ray will take us through the conceptual model.
My name is Ray, and I will introduce the entity relationship diagram of Spotify. In this ERD, there are total four relationships, and each relationship has different participation constraints and cardinality constraint. As we can see, in the Spotify ERD, user creates playlist has one-to-many relationship, which means one user can create many playlists. User as an entity has identifier attributes user ID and email, and the normal attributes username, password, date of birth, and country. Playlist is a weak entity in this relationship because in the Spotify database, you can make all your playlists available to the public. You are allowed to name your playlist that already exists in the database. For example, the playlist you create can be used by other users. For this reason, playlist is a weak entity type in the model and is identified by the user ID. Playlist has identifier playlist ID and normal attribute playlist title. In the relationship, playlist contains song as one-to-many relationship. Playlist as a weak entity is identified as user ID and playlist ID. Song entity has identifier attribute song ID and the normal attribute song order, song name, genre, and length. Also, a total participation constraint in the playlist entity means a playlist must contain one or more songs, and partial participation constraint in the song set means a song may be contained in a playlist. In the relationship, song performed by artist has many-to-many relationship. Entity song has the identifier attribute song ID and the normal attribute song order, genre, song name, and length. Entity artist has the identifier attribute artist ID and normal attributes artist name, album name. Also, a total participation constraint in the song entity side means the song must be performed by one or more artists. And the total participation constraint in the artist side means an artist may perform one or more songs. In the relationship, album contains songs has one-to-many relationship. Entity song has identifier attributes song ID and normal attributes song order, genre, song name, and length. The album entity has a composite identifier attribute album name and artist ID. In the very beginning, we thought album ID would be the identifier attribute. Then later we discovered it was not the case because we would not allow for multiple artists to be on the same album. This conflicted with the key constraints. To solve that, we created a composite identifier attribute using both album ID and artist ID. Also, a partial participation constraint in the song entity side means an album may contain many songs, and total participation constraint in the album side means a song may be contained in an album. Kavya will introduce the relational model based on the Spotify ERD we created. Thank you for listening.
Hey, I'm Kavya. I'd like to explain the relational model of our project based on Ray's conceptual model mentioned. So, as per the entity relationship diagram, this is the logical database modeling. Let me explain the conversion process. So, initially we process the normal entities from the ERD. Each normal entity becomes a relation in this model with all the simple attributes. Identifier attributes become the primary keys to the respective relations. Next, we usually check for the weak entities. As per our ERD, the playlist entity here holds the weak relationship with the user entity. So, for every weak entity, the primary key will become the partial key of the weak entity plus uh, identifying attribute of its owner. So, in this case, playlist ID plus user ID becomes the primary key of playlist table. So next, let's check if there are any 1 to m relationships in the ERD. So yes, we have three 1 to m relationships: user and playlist, album and songs, as well as playlist and songs. For example, one user might have many playlists. So every 1 to m relationship becomes a foreign key. So for here, for example, the user ID from the user table, this becomes a foreign key in the playlist table. Similarly, the album ID becomes a foreign key in the song table, and etc. So next, let's check for any M2M relationships. And yes, we have one M2M relationship which is artist and song. So it's like many artists can perform many songs. So therefore, we have a new relationship which is called performance. So performance has the identifier attribute from both artist and song. So that becomes a composite primary key in here, and they individually acts as foreign keys to each of the tables, artist and song tables. And we also notice that there is no one to one relationship, no unary or ternary relationships, no subtype supertypes, as well as no multi-valued attributes. So let me just break down the relations. Here we have six: user, playlist, song, artist, album, and performance. Let me briefly explain the contents of each of these tables. User table. User table saves the details like username, a not null unique user ID, which is a primary key here. It also saves password, date of birth, the location of the user. Additionally, we could also save the profile picture as a link. Saving the whole image might be a load to the DB, so instead we'll host the image maybe in the cloud and save its name or the link here in this table for the direct access. Next, let's go to the playlist table. Playlist table, each row of this table saves a unique non-null primary key, which is playlist ID, which is a primary key here, yes, and a non-null playlist title, the user ID from the user table. Here, user ID is a foreign key, a timestamp of when this playlist is created, as well as a song ID. Song ID again uh, becomes a foreign key to the song table. So a user can create zero or more playlists, uh, and a playlist can have zero or more songs. Next, let's talk about song table. Each row of this song table stores a detailed information regarding song of a particular album, including in what order it was added with respect to the other songs. So here the song order decides the order of the track on the specified disk. So this table saves song ID, which is a non-null primary key, song name, genre, playlist ID, album ID, song length, and the song order. Here, album ID is the foreign key to the album table, and playlist ID is the foreign key to the playlist table. Next, let's talk about the album ID. So, as the name says, album table consists of the details all about the albums in our database. Details like album ID, which is again a non-null unique primary key, an album name, which is also a non-null attribute, and its respective artist ID is stored here. Talking about the last table, which is performance table. So, like we spoke before, song and artist share a M2M relationship. Therefore, to convert them to a relation DB, we started a new entity called performance, which stores the primary key of the both entities, which is song ID as well as the artist ID. The primary key of this new entity is a combination of both these ID. So it is probably like a composite key, and each of this song ID and artist ID acts individually as a foreign key to their respective tables.
Hi, my name is Patty, and I'm going to review our physical model diagram and the overall explanation of how that went for our team. So on just the general overview for the diagram, you can see our user table, our playlist table, song table, artist, and album. We also had a performance table, and that was because we allowed for multiple artists to perform on multiple songs, so we had to have a way to keep track of that. In terms of things that went wrong with the physical model once we started building it, other than the general typo errors that I'm sure everyone experienced and encountered, Mostly we ran into constraint problems. So the first was with our album entity. We'd made album name a primary key, which prevented multiple artists from being added to the same album. So to solve for that, we created a new attribute called album ID, which had the added benefit of streamlining the process of uniquely identifying albums, which didn't involve having to type out the whole album name every time. And then we made album ID a composite primary key with artist ID, which allowed us to add multiple artists to the same album. We ran into a similar issue with the playlist table. We'd made playlist name a primary key, which prevented separate users from using the same title for their playlist. And that was an issue because everyone knows that it's common to have a workout playlist or to have a Christmas party playlist, and we needed to allow our users to name their playlist whatever they wanted, regardless of whether that name already existed in the database. So we solved that in a similar way. We just created a playlist ID attribute, made that the primary key. We still kept playlist name so that we could keep track of that, but we didn't need to make any composite key there. And then we did create an accidental feedback loop of error when we were creating our artist and album tables. We wanted to make sure that they would reference back to each other, and we just added too many constraints with that. So artist wanted to reference album, but the album table didn't exist yet, and album wanted to reference artist, and that table didn't exist yet. So we just needed to delete a constraint there, and realize that we could refer with just the one constraint, and that worked out just fine. So just to look over some sample data, this is sample data for user IDs, where we were able to put in a username, password, date of birth, email, and country of origin. We have a song table with sample data of the songs that we were able to enter in, including genre, length, the album they're associated with, song name, and then song order, which I'll talk about in a second. In terms of our artist, album, and performance tables, the important thing to us here was that we were able to list multiple artists on the same album. So on here you can see two artists on the same album ID, and then two artist IDs on the same album, and then over here, two artists that worked on the same song. It was important to us to have those kinds of duplications be allowed, because in the real world, multiple artists do work on the same song or in the same album, so we needed that to be reflected in the database. And then finally, we have the playlist table, which just records the playlist ID and then playlist title, and each one is uniquely identified to a user ID. And then the song order that I mentioned earlier is so that when people build their playlist and they build it in a very specific order, the database needs to capture what that order was, so that if they decide to rearrange it and group it by artist or group it alphabetically later, if they want to go back to their original order that they added the songs in, they can always do that. So that's what the song order query shows, is that we were able to capture that. Thanks so much. I think that's everything that I had on the physical model.
This concludes our presentation on Spotify. Hopefully this presentation helped increase your understanding of how a service like Spotify works. What we learned was that many of the technologies that we use every day and take for granted are quite complicated, and they're incredible works in database management. Even simple operations like creating a playlist and retrieving the music on it have to be designed and executed in a specific manner. Despite the complexity, however, we learned that something as grand as Spotify can be built brick by brick from the conceptual model through the physical model. Thank you.